Welcome back everyone. So now in this video we are going to discuss about quality of service and the techniques to improve quality of service. So quality of service or QoS is an inter-networking issue that has been discussed more than it is defined. Like we all need quality, we all need service that's very good, but still if we want to define it, then it is something a flow of data seeks to attain. Like every data seeks to attain the quality of service. And when we are talking about flow, we have four characteristics of flow. The first is reliability, second delay, third jitter, and then bandwidth. So when we are talking about reliability, so reliability is a character that a flow needs. Like lack of reliability means losing a packet or acknowledgement. If a data is not reliable enough, so how do we know that the info we are sending, is it even reaching the receiver or not? So however, the sensitivity of application programs to reliability is not the same. For example, emails and file transfers needs high reliability than any audio call. So if any packet of data is missing from an email, so there's no use of that email, and same with file transfer. And after that we have delay. So in this case, telephony, audio conferencing, video conferencing need minimum delay, while delay in a file transfer or email is less important. Like when we are talking to someone, so there should not be any delay in talk. And when we are transferring any file or an email, so even if it takes time, it's okay. Even we can get an example from YouTube. So if you have observed carefully that the YouTube algorithm works in a way that if we are commenting something, the comments will be shown, but the likes update slowly. Like we have big YouTubers, and we can observe this phenomena on their videos, that when sometimes there are more comments than there are likes in that video. And then we have jitter. So jitter is the variation in delay for packets belonging to the same flow. For example, if 4 packets depart at time 0, 1, 2, 3 and then arrive at 20, 21, 22, 23, all have the same delay, 20 seconds. On the other hand, if the above 4 packets arrive at 21, 23, 21 and 28, they will have different delays, like 21 seconds, 22 seconds, 19 seconds and 24 seconds. And for applications such as audio and video, the first case is completely acceptable, but the second case is not. For these applications, it does not matter if the packet arrives with a short or long delay, as long as the delay is same for all the packets. But it's not true for the second case. Then we have bandwidth. So for example, different applications need different bandwidth. Like in a video call, we need to send millions and millions of bits per second. And on the other hand, the total number of bits in an email may not even reach a million. So there's a lot of difference in bandwidth. Now let's cover the techniques to improve quality of service. So there are 4 techniques to improve quality of service: scheduling, traffic shaping, resource reservation, and admission control. Scheduling has 3 types: FIFO, first in first out queuing, then priority queuing, then weighted fair queuing, and traffic shaping has leaky bucket algorithm and then a token bucket algorithm. Now let's discuss them one by one. So first it's scheduling. So packets from different flow arrive at a switch or a router for processing, and a good scheduling technique treats the different flows in a fair and appropriate manner. Like we have FIFO, first in first out queuing. The packets wait in a buffer. Here in FIFO, the packets wait in a buffer, which is also known as a queue, until the node, the switch or the router, is ready to process them further. So they will arrive. If the queue is full, they will be discarded. But if a queue is not full, they will go in this buffer, and then when the processor, the router or the switch, is ready, they will process it further. First in, first out. Then we have priority queuing. By the name itself, we can see there's some priority in that. So here packets are first assigned to priority class. Each priority class has its own queue, and the packets in highest priority queue are processed first, and the packets in the lowest priority queue are processed last. Like we can see here, packets arrive, then there is a classifier. It classifies the packets into higher priority packets or lower priority packets. Then if the queue is full, they will discard the packet. But if the queue is empty, then the packet will come here in the queue or the buffer, and then the processor, the router, will make it ahead. Same for the lower priority queue. But there's a drawback. If the higher priority queue is always full, the lower priority queue would not even get a chance to get processed further. If the higher priority queue is always full, then the lower priority queue will not even get a chance to process further. Then comes weighted fair queuing. So in this technique, the packets are still assigned to different classes and admitted to different queues, but here the queues are weight based. Weight based means higher weight means higher priority. But this weighted fair queuing happens in a Robin Hood fashion. So we know who Robin Hood was, right? So Robin Hood was a person who even gave something to the poor. And here what happens? So for example, this is the classifier. Packets arrive in the weight 3, 2, 1. So for example, if the weights are 3, 2 and 1, 3 packets are processed from the first queue. At one time, 3 packets are processed from the first queue. Then 2 from the second, then 1 from the third. So every weight is getting an opportunity to go ahead. This system does not impose priority on the classes. So if this system does not impose priority on the classes, all weights can be treated equally. And this way we can have a fair queuing with priority. Data. Then this is Robin Hood style fashion ticker. This will take 3 packets here, it will process it further, 2 packets from here, process it further, and then 1 from the lowest priority and then process it further. But everyone is getting their chances. So now let's discuss about traffic shaping. So traffic shaping is a mechanism to control the amount and the rate of traffic sent to the network. And we have 2 algorithms here. The first is leaky bucket algorithm. So we'll try to understand this leaky bucket algorithm by this analogy. So we have a tap. When we open the tap, the water flows, but the water is just like a bursty flow. Sometimes there is a lot of pressure from the tap and sometimes there's not. And that's what happens here. Then we have a bucket and we have a hole in that bucket. Water will be flowing like sometimes fast, sometimes slow into that bucket, but the water from the hole will be flowing with a fixed flow. This is what happens in leaky bucket. So as we can see here, for 2 seconds, the data is flowing at 12 MB per second. And for the next 1, 2, 3, 4, 5, nothing is there. But again, for the next 3, the data is flowing for 2 MB per second. This is known as bursty data. So if we calculate 12 into 2 and then 2 into 3, we'll get 30 MB per second, the whole data which it has processed. Then what leaky bucket does is that it shapes the bursty traffic into a fixed rate traffic by averaging the data rate. As we can see here, we had 30 MB per second, and here we are processing the data by 3 MB per second for 10 seconds. So we again have 30 MB per second. But there's one drawback. It may drop the packets if the bucket is full. As we can see here, we are arriving, the data is arriving. If the queue is full, the buffer is full, it will discard. If it's not, it will go inside the queue or the buffer, and then the leaky bucket algorithm will remove packets at a constant rate. So to overcome that, we came up with token bucket algorithm. So as we can see here, we have a bucket, but inside that bucket we don't have packets, we have tokens. So we have tokens here instead of packets. So the token bucket allows idle host to accumulate credit for the future in the form of tokens. So here we had two problems. First, we were not crediting the idle host. The host here was idle, it wasn't doing anything, but we didn't credit him, did we? So that's why we had two drawbacks. First was this credit, and then the second was that it may drop packets. So we overcame here both of those drawbacks. So for example, so what happens here, that if so the data is processed in terms of tokens, and if the bucket is full, it won't accept any more data. So the loss of data is impossible, as data doesn't arrive here. Data arrives in the form of tokens. Tokens arrive here. Then if the bucket is full, the tokens won't be uniformed, right? So there is no loss of data. Then the tokens go inside the queue, and then they are processed further. For example, if we take a real life analogy, so if you are going to a movie, then you need token or tickets, and only people with tickets can go ahead. That's what's happening here. So there is no loss of data, and we have token mechanism. Now let's go to the other side and read about the remaining. So third is resource reservation. So a flow of data needs resources such as buffer, bandwidth, CPU time, etc. So that all is handled by resource reservation. And then the fourth one is admission control. So admission control refers to the mechanism used by a router or a switch to accept or reject a flow based on predefined parameters known as specifications. So admission control refers to a mechanism used by routers, like it can accept or reject a flow based on some parameters, like we have that only data which is arriving at more than 5 Mbps will be accepted. Anything less than that will be rejected. So that's taken care of by admission control. And before a router accepts a flow for processing, it checks the following specifications to see if its capacity in terms of bandwidth, buffer size, CPU speed, etc. In the previous comments, two other flows can handle the new flow. That's what I right now just said. So now we have completed our topic, our whole chapter basically, and I hope that we enjoyed, and thank you very much.